day 3 on Unit 4, electron configurations. So today we're going to talk about how to write those electron configurations, which we've already done, and write those electron configurations including monatomic ions. And remember, ions have a charge, which means a different number of electrons. We're going to write the noble gas abbreviations, which I call shorthand, using the electron configuration that we learned yesterday. We're going to classify those elements based on the outermost electron configuration, which we'll talk about. And then we're going to talk about valence electrons. So let's take that periodic table that we've already filled in on Thursday. We did it together. And remember, these are the principal quantum numbers, the energy levels. 1, 2, 3, 4, 5, 6, 7. It's S at the moment because this right here is the S sublevel. Here is the P sublevel, 2P, 3P, etc., 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 etc. Here is the D's right here, which we already know, we talked about. Here's F's. So we're going to allow a box to represent an electron. And we're going to read the periodic table from left to right, which we have already done. Read it like a book. Nitrogen. Go ahead and give me the electron configuration for nitrogen. We did this last time. Did you come up with 1s2, 2s2, 2p3? Here is 1s2, reading like a book, 2s2. And then over here it'd be 2p1, 2p2, 2p3, right there behind this box. That would be nitrogen. Chlorine. Go ahead and pause the video and see if you can write chlorine's electron configuration. Did you come up with 1s2, 2s2, 2p6, 3s2, 3p5? And remember, you can always add the electrons together. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 5 is 17. Now let's look at ruthenium, Ru. That has 44 electrons, or the atomic number is 44. Go ahead and give it a try for electron configuration. Pause the video and give it a try. Did you come up with this? So, how to write the noble gas abbreviations, or like I like to say, the shorthand, because who wants to write out, unless you're told to do so on the test, those long electron configurations for each element when it gets up to ruthenium, or when it gets up to even higher than that, like xenon, for example. It takes a lot of time to do that. So we're going to do that by first putting forth the a noble gas, and I'll explain. But first, let's go to column or group 18, which is to the right of the periodic table, and look at the noble gases because they're so noble. We have helium, neon, argon, krypton, xenon, radon, and UUO, element 118. Pick the closest noble gas to the element that you are writing the electron configuration for, the one that you are looking at, that comes before that element. Let's do an example. Potassium, K, that has 19 electrons. So we would write the closest noble gas to that, which comes before the element of choice, and that is argon. We would write the element symbol AR. We'll put brackets around that, and that represents all the electron configuration up to argon. Then we're going to keep going like reading a book on the periodic table and put 4s1, which is potassium, and this is the shorthand or noble gas abbreviation for potassium. A lot less to write, isn't it? Let's do another example. Magnesium. Magnesium has 12 electrons. So we're going to look on the periodic table and find the closest noble gas, which would be neon, which has 10. So we would put Ne, the atomic symbol for neon, put brackets around it, And then keep reading the periodic table like a book. Go on to the next energy level. We have sodium, then which is 3s1. Then we have magnesium, 3s2. So this is the noble gas abbreviation for magnesium. Neon, brackets, 3s2. Let's do BK, which is berkelium, which is located in the F sublevel. It has 97 electrons. So the closest noble gas would be Rn, radon, 86 electrons. So we would put Rn, brackets, 7s2, keep going, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 5f, 9 electrons. That would be the shorthand or noble gas abbreviation for berkelium. Now let's talk about ions. Remember that elements will lose or gain electrons to obtain the same number of electrons as a noble gas, which makes them ions. Because we're changing the number of electrons, protons will stay the same. Protons positive, electrons negative, and we will have a different charge on that element. So if two atoms have the same number of electrons, they are said to be isoelectronic. Let's look at that, because that's a cool word. Let's write the electron configurations for some ions. Here is O negative 2. So obviously this has a charge, oxygen has a charge of negative 2, which means it has 2 extra electrons, right? Because it's a negative charge, we have more electrons than protons. O negative 2 is isoelectronic with neon. Because if we look on the periodic table, we'll find oxygen. Oxygen has 8 electrons, but if we gain 2 more, 9, 10, we look like neon. We look like neon, but we're still oxygen. So, like I said, although O negative 2 and neon have the same electron configurations, they are not identical. So the electron configuration for O negative 2 and neon is the same. 1s2, 2s2, 2p6. Count the electrons. 6 plus 2 is 8, plus 2 is 10. Oxygen has 8 electrons, plus 2 more because it's a negative 2 overall charge, which gives me a total of 10 electrons. So O negative 2 is this electron configuration. Valence electrons. Valence electrons simply means the electrons located in the outermost energy level. So when you write your electron configuration, it is the highest energy level that you have, and those electrons are located in the outermost energy level. That's responsible for bonding, meaning the reactions take place on the outermost shell, the outermost energy level, those outermost electrons. So to count the number of valence electrons in the electron configuration, you must look at the highest number energy level in the entire configuration, like I just said before. Then you add those electrons together, those electrons only in the highest numbered energy level. Let's look at an example. So let's write an electron configuration for the ion Rb plus 1. That's rubidium. It has 37 electrons. But it says plus 1, which means one of those electrons were taken away because there now is a positive charge, which means more protons than electrons. So rubidium looks like krypton, because if you take away an electron, you now have 36 electrons, and krypton has 36 electrons. So rubidium plus 1 is isoelectronic with krypton. Its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. That is a filled outermost energy level, sublevel of 4p6, and that is krypton. So even though rubidium has 37 electrons, it looks like krypton now. Its outermost shell is filled, which means it looks like a noble gas. It is more stable with the outside or the outermost electron shell filled. Give the electron configuration and charge. Well, given that information, give me the ion. So if we have 1s2, 2s2, 2p6, you following along on the periodic table, that looks like neon. But we have a 2+ charge. Here's the other example, but let's keep talking about the example number 1. If it has a 2+ charge, that means we took away 2 electrons. So magnesium, take away 2 electrons, that's 12, 11, 10. We look like neon. But we are still magnesium with a 2+ charge. Let's look at this 1s2, 2s2, 2p6. Follow along in your periodic table. 3s2, 3p6 with a -3 charge. So we look like argon, but we have a -3 charge, which means we added 3 electrons. So which element do you think added 3 electrons to look like argon? That would be phosphorus. And we would say P -3 because it has an overall charge of -3 to give me 1s2, 2s2, 2p6, 3s2, 3p6, which is the electron configuration for argon. But it's also the electron configuration for the ion phosphorus -3. So simply put, when doing ions, you do the normal electron configuration and you focus on the electrons. How many electrons do I have overall? So, how many valence electrons are in each of the following configurations? Potassium. It has 19 electrons. So let's give the electron configuration, which we've done before. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Remember, the valence electrons are only in the outermost shell, the highest energy level, which in this case here would be 4, because all these are lower energy levels than 4. This is the 4th energy level in the valence shell, which means outermost shell of where the electrons are found, the outermost layer, if you want to think of it that way. The outermost energy level where electrons are found is represented by the principal energy level of 4. And then this has 1 electron in the upper right corner. Remember that represents electrons. It has 1 valence electron. So all we do for valence electrons is count the electrons in the highest energy level given for each element. Let's do an example of cobalt. Cobalt has 27 electrons. Right, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. If we add all those electrons together, we get 27. Notice how 3d7 is a higher energy, but it's not the highest energy level given. That's 4. Even though 3d7 is on the right of the 4s2, and it does have more energy because it's a bigger sublevel. D has 10 electrons maximum. 4s2 is still on the outside because it is the highest energy level given, not 3, 4. So we would find the highest energy level, which is 4. Look at that, and we have 2 valence electrons. So cobalt has 2 valence electrons. Let's do neon. Neon is 10 total electrons. 2 plus 2 plus 6 is 10. 1s2, 2s2, 2p6. Notice how there are 2 sublevels given for neon in its outermost highest energy level, which happens to be the energy level of 2. So 2 is the 2nd energy level, and it is the valence shell, the outermost shell where electrons are found around the nucleus of neon. And we will just simply add those together, which would be 6 plus 2, 8 valence electrons for neon. go ahead and do or start worksheet 3. Have fun.